This video will be focusing on the graphing of exponential functions. An exponential function is when we have something called a base being raised to some power. So it kind of looks like this right here. F of x equals 2 to the power of x. In this function, 2 is the base and x is the exponent, so something to a power. Now, I first want you to create a table of points, and we're going to plot those points on our graph to see what the general shape looks like. When we are creating a table, I'm just going to use -2 to 2 for my x values, and to get the y values, or the f of x column, we just plug it back into the function. So f of -2 would be where I plug in a -2 wherever I see an x. So 2 to the power of -2. If something is raised to a negative exponent, we would move it from the numerator to the denominator, or the denominator to the numerator. So right now, 2 is technically in the numerator because I can write it as 2 over 1. Meaning that I need to move it down to the denominator. So 1 over 2 squared. The act of moving it down makes it the exponent positive, and the 1 just serves to be a placeholder. That gives me 1 over 2 squared, which is 4, so 1/4. Meaning that the first point that we have is -2, 1/4. F of -1, once again, we plug in a -1 wherever we see x. And because it's negative, we're going to bring it down. So 1 over 2 to the first power, or that's just 1/2. Meaning -1, 1/2 is our second point. F of 0 gives me 2 to the 0 power. Anything to the 0 power will always equal 1. And you're going to see this idea a lot throughout this unit. So again, anything to the 0 power equals 1. In fact, I'm going to write that up here. Okay. F of 1, so 2 to the first power. Anything to the first power is just itself. So 2 to the first power is just 2. F of 2, we have 2 squared, which gives me 4. So our other points were 0, 1, 1, 2, and 2, 4. Let's go ahead and plot all 5 points in the coordinate plane. So I got -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. You can see that these points create a curve rather than a straight line. And as the x values increase, this function is going up forever. As the function decreases, so the x values decrease, it actually is not going to go down forever. It's going to get closer and closer and closer to 0, but it's never quite going to touch it. So when something gets infinitely close to something else but never touches it, we call that an asymptote. Okay, so I'm just going to write that there is an asymptote at the x-axis, which in this case is y equals 0. Something else I want you to notice is the domain and the range. The domain will always be all real numbers because we can see going from left to right, it's always going to continue as we move left towards negative infinity, and the function will continue forever as we move to the right, so towards positive infinity. Remember, if we were using something called interval notation, we do left to right, parentheses for not included, brackets for included. So infinity and negative infinity are not included. We can't actually reach those. That's why I put the parentheses. For the range, it must be down to up. So domain is left to right. Range is down to up. The lowest this graph will go is 0. Now, a lot of people say, okay, it's a number, let's put a bracket. However, is 0 included? Will it actually ever touch 0? No. So it actually needs a parentheses here. It's going to go from 0 all the way up towards positive infinity, which also needs a parenthesis because we cannot obtain that. This function is called an exponential growth function. An exponential growth function is when the base is greater than 1 and the function increases as x increases. If the base is between 0 and 1, it's an exponential decay. And that would mean that the function is going to decrease as x increases. We're going to take a look at example 1 and determine, is it a growth or is it a decay? Parts A and B are written in the form f of x equals a times b to a power of x. So a is the number out front if there is one. B is what's being, it's our base, it's what's being raised to the power. And then x is the actual power. So here, for part A, I have 1.5 to the power of x. So that 1.5 is our base. Since there's nothing out front, so no number times this, it's just going to be 1. Okay? All right, well, just by looking at this, I can tell that b is greater than 1. So if it's greater than 1, that means it's an exponential growth. However, when I take a look at part B, A is 30 and B is 0.8. Now, 0.8 is between 0 and 1. So that means that this is a decay. If you were just given a graph, we can tell by how the function behaves as x increases. So as x increases, what happens? For part C, as x increases, the function gets closer and closer and closer to 0. So this is a decreasing function, which means that this is a decay. And in part D, as x increases, the function itself is also increasing. It's going up higher and higher and higher towards positive infinity. So this is an exponential growth. Notice how these graphs also have asymptotes. They both also have a domain of all real numbers, and they both have a range from 0 to infinity. I would like you to try this problem where you circle the growth functions and box the decay functions. I also would like you to try this one where you write your own equation. Hit play when you're ready. In the first try problem, there are multiple growth functions and only 2 decay functions. So everything's actually growth except for this function right here where the base is 1/5. And this one right here where the base is 0.3. A common mistake is that whenever people see fractions, they think that it's going to be a decay. However, 7/2 is greater than 1. And then here we had 4/3, which is also greater than 1. Everyone's answers for the second try problem could look different. I just did something where I did include a values. I didn't have to. I could have easily just put 2 to the power of x and 1/2 to the power of x. Just make sure for the growth your base is greater than 1. And for the decay, your base is between 0 and 1. The base must be what's being raised to the power. In real world problems, an exponential growth and decay function usually looks something like this, where we're looking at simple interest. The a of t represents our total amount. The a sub naught, so a at time 0 is our initial or our starting amount. The r is our rate, which we have to express as a decimal. And then t stands for time. So if I tell you that there's a 7% increase, then inside of the parentheses, we're going to have 1 plus r. 1 stands for 100%, and then we had a 7% increase. Now we can't put 107 right here. What we need to do is 1 plus 0.07, so 1.07. Remember, when I give you a percent and you need to convert it as a decimal, you take the decimal, which is at the end. This is currently 7.0, and you move it to the left 2 places. That's how I got the 0.07. And with a decrease, it would be 1 minus 0.07. Example 2 says, and I'm going to underline everything that's important as I go along. Tony purchased a rare 1959 Gibson Les Paul guitar in the year 2000 for $12,000. Experts estimate that its value will increase by 14% per year. Write a function to model the growth and the value for this guitar. So I'd say growth is another keyword there. If I were to try and plug it into our equation, total amount equals initial amount times 1 plus or minus the rate raised to the power of time. I don't know what the total amount is right now because I don't know what year we're looking at, but I do know that initially when the guitar was first purchased, it cost $12,000. So 12,000 is the a sub naught. So I have a t equals 12,000. In parentheses, I'm either going to have 1 plus r or 1 minus r. Because it's a growth, I know it's going to be 1 plus. And the rate needs to be expressed as a decimal. So 14% will actually be, moving the decimal to the left 2 places, 0.14 raised to the power of t. So really my function is a of t equals 12,000 times 1.14 to the power of t. It's important you know how to write this because if I would say, what is the amount after 5 years? So in the year 2005, all you would have to do is plug 5 in where you see the t. When I plugged 5 in for t, the amount was $23,104 $1,000,097. So that means in the year 2005, this would be the value of the guitar.